Today, I want to continue talking about sequences, series, and power series. We had our one-word definitions of sequence, series, power series. A sequence is a list, and a sequence converges if the terms have a limit. A series is a sum. A series converges if the sum is finite. A power series is a function where the inputs are real numbers and the output is a series. And so our question is a little different. For what values of x does the power series converge? That's a different question. It's not does it or doesn't it. What values of it, for what values of x does the power series converge? So I'm going to recycle the problem that I couldn't seem to put together yesterday. Let's say we have a power series that looks like the sum of 3 times x to the n. We get the sum of 3 times x to the n. So 3 plus 3x plus 3x squared plus 3x cubed, and so on. That's a power series. There's an x in it. We can pick a value for x as an input, and the output is a series. So if I choose the input of 0.1, then I get 3 plus 3 times 0.1 plus 3 times 0.1 squared plus 3 times 0.1 cubed, and so on. So the output is a series. The question is it okay to plug in 0.1 into this power series? Does it make sense? Do we get a series that converges? And in this case, we do. So here, so we're asking, here's a series, does it converge? And we can see that it's going to, because I have 3 plus 0.3 plus 0.03 plus 0.003. And this will go on forever. So we're getting 3 1/3, 3.3 repeating. So this power series converges for x equals 0.1. The series converges and the sum is 10/3. So we can conclude that the power series converges when x equals 0.1. For other values of x, the power series might not converge. So if we take for an input 2, now we're going to get a power series that does not, or we're going to get a series that does not converge. Once again, here's an input, and our output is a series. It's infinitely long sum. This sum is going to be infinite. It's just going to continue to grow. So this series diverges. So our original power series diverges when x equals 2. Yesterday, we talked about the brute force way to find out if a series converges, and that is looking at the sequence of partial sums. In this first example with the point 1, if we look at the sequence of partial sums, the first term will be 3, and then the next term in the sequence will be 3 plus 0.3 or 3.3. Then the next term is 3.33, and then 3.333, and so on. So we can see that the sequence of partial sums converges. The limit of the sequence of partial sums is 3 1/3. And so you'd say that the sum of the series is 3 1/3. So the sequence of partial sums, this list that has a limit. So the series converges. The sequence of partial sums converges, so the series converges. The sequence of partial sums in the second example, where x is equal to 2, will be 3, and then 9, and then 18, 21, and then 45. So that sequence of partial sums is clearly just going to grow. And so the limit does not exist. So the limit of the sequence of partial sums here does not exist as the terms go to infinity. Questions? So series are what we're going to get when we take inputs and plug them into power series. We want to think of power series. We want to use power series to represent functions, either functions that we already know to help understand them better, or functions that we don't know what they are. But we can come up with a power series description for that. So we have to become able to look at a series and determine if it's going to converge or diverge. And so that's the big thing that we need to talk about. So we're talking about a series, we put a sigma and then the name of the term, so sigma an, and that's going to be a series. We're not going to worry about this where the series begins. If we're talking about convergence, then we must be talking about infinite series. So we're going to save ourselves a little time and not be specific about the index. All right. The tools that we have available are, of course, like we saw, the sequence of partial sums. If the sequence of partial sums converges, then the series converges. So if the sequence A1 plus A2, A1 plus A2 plus A3, if this series converges, then the series converges. The limit of the sequence of partial sums will be the sum of the series. So what we want to do now, is write down all the things we know about convergent and divergent series, things that we can identify. And here's the first thing that we're going to pick. So if we have a series, the first thing that we can look at, the easiest thing to check, is if the limit of the terms of the series is equal to 0. Sometimes this is referred to as the test for divergence. So we have a series. And here's the test for divergence. If the limit of the terms is not 0, then the series diverges. When you're looking at a series, if the terms don't go to 0, then the series diverges. This makes sense when we think about the sequence of partial sums. Let's look at an example. So here we have a series. And the terms are 7 plus 2n over 5 plus 3n. So I got 7 fifths plus 9 eighths plus 11 elevenths plus 13 14ths plus 15 17ths and so on. We're trying to add up all these fractions. Since the limit of the terms is not 0, since the limit of the terms is not equal to 0, the series diverges. If we think about large values of n, the fractions just look more and more like 2/3. That's what we're saying down here. Limit of the terms is equal to 2/3. As n increases, the terms get closer to 2/3. So for large values of n, this sequence looks like, or this series looks like plus 2/3, plus 2/3, plus 2/3. So eventually, the sequence of partial sums, whatever it is in this section here, the next one is going to be s plus 2/3. And then the next term in the sequence of partial sums will be s plus 2/3. And then we'll have 3/2. So in this sequence, the next term is 2/3 more than the previous term. And so that's going to be a sequence that grows without bound. In the long run, if we just start plotting all the term or the sequence of partial sums, we'll start seeing a line with a slope of 2/3. Won't be a line because we're making a sequence of this discrete list. There's nothing in between, but it'll be a bunch of dots on a line with a slope of 2/3. So this is the first thing that we want to go for. If the limit of the terms is not 0, then the series diverges. Now we get to the fun part of sequences, series, and power series. All we're saying is that if the limit of the terms is not 0, then the series diverges. That does not mean that if the limit of the terms is 0, the series converges. All we're saying is that the limit of the terms is not 0, then the series diverges. Any questions? Yes.
What do you mean by that is that it can't equal 0 and still diverge?
What do you mean by it?
By the equals 0.
What's it though? What's equaling 0?
And the limit of a.
Correct. When the limit of the terms can be 0 and the series still diverges. That's possible. Which highlights another one of our issues that we're going to have. You don't get to use the word it anymore. We're going to be going through all these tests for convergence, and a lot of them are going to involve limit as n goes to infinity. So if you start saying it doesn't exist or it is not equal to 0, even if I know what you're talking about, I'm going to say, what's it? And I'm going to be that dick. Please, why do you have to be so specific? Because I need to know that you know what you're talking about. It's the same, it's even more annoying when you're in a linear algebra class, because you'd be like, oh, it. I might call what's it? The system, the equation, the matrix, this vector, this set of vectors. So especially right now, be very careful about using the word it. So you are absolutely correct. If the limit of the terms is 0, the series might converge, but it also might diverge. So we're going to need something more better than this. If the limit of the terms is not 0, the series diverges, and we're done. If the limit of the terms is 0, then we have actual work to do. And we're like, oh, have to do some work. So it's really important to realize that this is a test for divergence. You don't run a test for divergence and then conclude something converges. That wouldn't make any sense at all. So it's possible that the limit of the terms of the series is 0 and the series still diverges. And we're going to look at our favorite example. So we're going to look at our favorite example of a series where the limit of the terms is equal to 0 and the series still diverges. Our favorite way to demonstrate this is to look at the improper integral. It's not going to fit down here. Let's consider the improper integral from 1 to infinity of 1 over x dx. Improper integrals, a new topic for us. I have not mentioned improper integrals before. What do you think makes this improper? What piece of this integral is making this improper? And it goes to infinity. It's like, oh, dude, we're supposed to make a definite integral. Those are supposed to be real numbers, not friggin' infinity. So that's the improper part. So if that infinity was trying to sneak into this definite integral, it rolled a 1 on its stealth check. We can't integrate something when there's an infinity. We can't plug in infinity. We can't find the antiderivative. We get the natural log and then plug in infinity. It doesn't make any sense to plug in infinity. So here's how we plug in infinity. So when we have the integral from 1 to infinity of 1 over x dx, We're like, oh, dude can't plug in infinity. Can't just plug in infinity. So what we do is we plug in infinity by doing this. So fine, we replace infinity with b and then look at the limit as b goes to infinity. That's how we plug in infinity, even though we don't call it plugging in infinity. Once you get through Calc 2 and probably Calc 3 as well, once you get through Calc 3 and everybody's on the same page, and you're talking to a bunch of people that have all been through Calc 3, you can talk about plugging in infinity, and it'll be fine. But until then, you don't get to say that. People will be like, oh, you can't plug in infinity. I'll be like, oh, well, actually, and it'll be really annoying. So just don't do that. Once you get through Calc 3, then it'll be fine. When you win 20 in the show, you can let the fungus grow in your shower shoes. Until then, it means you're a slob. I don't know if you've seen the movie Bull Durham, but it's a very good movie. Ostensibly a baseball movie, not really about baseball. So let's calculate this. I still haven't done this limit business, so it's still the limits as b goes to infinity. The antiderivative of 1 over x is the natural log of absolute value of x, and then we'll evaluate this from 1 to b. So I'm going to have the natural log of the absolute value of b minus the natural log of the absolute value of 1. But we still haven't done the limit as b goes to infinity. As b goes to infinity, the natural log of b also goes to infinity, so this limit does not exist. Natural log of 1 is 0, but natural log of b kind of wins. It's going off for. This was just a calculation of a definite integral. We can think about what this, how we can interpret this. One interpretation of this would be to think of the area under the function 1 over x we could think of this improper integral as representing the area starting off at 1 and going to infinity. think of this definite integral as an area, as we do, then we can say that this area is infinite. This result indicates that the area is infinite. We might be tempted to think, well, of course the area is infinite. One of the boundaries is infinite. But that's not good enough. We can have an infinite boundary still closing in a finite area. If I trade my 1 over x for 1 over x squared, you can make the calculation the same way. You make the calculation the same way. Replace infinity with the limit as b goes to infinity. That's how we plug in infinity, although we're not really plugging in infinity. The antiderivative of 1 over x squared is minus x to the minus 1, so we'll have the limit as b goes to infinity of minus 1 over b minus a negative 1 over 1. And now something different than the previous one happened. Now as b goes to infinity, negative 1 over b goes to 0. And so this limit does exist, and the value is 1. So if I replace that function, 1 over x, with the 1 over x squared, if I replace the x with the 1 over x squared, it looks like a very similar area. But this time we're saying that the area is equal to 1. Start off at 1 and get all this area. We have the function y equals 1 over x squared. Now it looks like our area, based on this calculation, is equal to 1. Any questions? I've pointed these two examples back to back. Not individual examples that matter, it's the sequence of examples that matter. The point of doing a sequence of examples is to make sure that your examples form a series, that they all add together to something. Don't just make a sequence of problems, make a series of problems. Does that make sense? All right. All right, so tomorrow we'll talk about what these improper integrals can tell us about series. That's going to do it for today. I'll see y'all tomorrow. Have a great day.